we shall introduce a vector operation called the scalar product or dot product that takes any two vectors and generates a scalar quantity or number. Let A and B be two vectors. Because any two non-collinear vectors form a plane, we define the angle theta to be the angle between the vectors A and B as shown in picture. Theta can vary from 0 to 180 degrees or 1 pi. The dot or scalar product of the vectors A and B is defined to be product of the magnitude of the vectors A and B with the cosine of the angle theta between two vectors. Note that we always write a dot between vectors in dot product. It is clear from definition of dot product that the scalar product is commutative. The scalar product can be positive, 0, or negative, depending on the value of cosine theta. For theta between 0 and 90 degrees, cosine theta is positive, which implies the dot product is positive. For theta between 90 and 180 degrees, cosine theta is negative, which implies that dot product is also negative. If the vectors A and B are orthogonal, which means that theta is 90 degrees, then cosine theta is 0, which implies that dot product between any two orthogonal vectors is 0. If the vectors A and B are codirectional or collinear, theta is 0 and cosine theta is 1, which implies that dot product between vectors A and B is product of only their magnitudes. Product of a vector with itself gives the square of the dot product of the vector because same vector is codirectional. We can give geometric interpretation of the dot product. The dot product between two vectors is based on the projection of one vector onto another. Let's imagine we want to calculate how much of vector A is pointing in the same direction as the vector B. In this case, we see that part of vector A that is pointing in the same direction as B is A cosine theta, which is the length of the shadow of vector A onto B. Now we can write the scalar product as in this formula, where we are multiplying length of shadow of vector A onto B with magnitude of vector B. So the scalar product is the product of the projection of the length of vector A in the direction of vector B and magnitude of vector B. Note that we can also calculate how much of the vector B is in the direction of vector A. This scalar product is the product of the projection of the length of vector B in the direction of vector A and magnitude of vector A. We can calculate dot product of vectors A and B in terms of their components. When we multiply components, we get very big expression, like this. Fortunately, many terms can be eliminated. The dot product between a unit vector and itself is simple to compute. In this case, the angle theta is 0 and cosine theta is 1. Given that the vectors are all of length 1, the dot products are all 1. Since the standard unit vectors are orthogonal, we immediately conclude that the dot product between a pair of distinct standard unit vectors is 0. Now we can simplify the dot product formula to the following expression. We get to this expression by eliminating following terms. X roof and X roof scalar multiplication gives 1. X roof and Y roof is 0, X roof and Z roof is 0, Y roof and X roof is 0, Y and Y is 1, Y and Z is 0, Z and X are 0, Z and Y are 0, and Z and Z are 1. So we are adding only these terms where scalar product is 1. And that is how we get the final expression for scalar product. Work is an important physical example of the mathematical operation of taking the dot product between two vectors. Suppose we are pulling a body along a horizontal surface with a force F. We obviously do some work by moving this barrel. First, we choose coordinate system such that the horizontal direction is in the x-axis and the force forms an angle theta with the positive x direction. It is convenient to decompose a force F in f of x and f of y component vector. When a constant force undergoes a displacement, delta x along the x-axis, only the component of the force along that direction, in our case that is f of x component vector, contributes to the work. Logically, we can see that the work is directly proportional to the magnitude of vector f of x and the magnitude of displacement vector, so we can write work as a product of these two magnitudes. We can get to this formula also by using the dot product. We can write the force vector F in terms of unit vectors as F of x times x roof plus F of y times y roof, and the displacement vector as a magnitude of vector delta x, or distance traveled, times x roof. The scalar product between the force vector F and the displacement vector is given by the following expression. Here we have dot product between x roof and x roof, which is 1, and dot product between y roof and x roof, which is 0. That means that result is f of x times delta x. And this is the same result as previously. The work done by the force is then as in following expression.